Okay, in this video we're going to take a look at a rational function that has a slant asymptote. Now, if you remember slant asymptotes from your pre-calculus class, I would suggest you pause the video and try to graph this, finding intercepts, asymptotes, lose my train of thought, maxes and mins, points of inflection, and making sure that you respect the intervals of increase, decrease, concave up, concave down, etc., etc. Okay. If you don't remember that, I'm going to start by finding the slant asymptote here. Once we've done that together, I would suggest you then pause the video and do the rest of it on your own and then tune back in to see how you did. Okay. A slant asymptote is going to happen when we have a function that is rational. So it's just a polynomial over a polynomial, and the degree on top is equal to 1 plus the degree on the bottom. Okay. So the degree on top has to be bigger, but it has to be bigger by exactly 1. And that's what we have right here. Now, as we go about finding the asymptote, we'll see why that criterion holds. Okay. I will just point out, if there is a slant asymptote, there is no horizontal asymptote. Because notice, if I look at the lead terms, x squared over x would reduce to x. That's going to go off to infinity or off to negative infinity. So if there's a slant asymptote, that's describing the end behavior, and it's going to be a slanted line so that it's going to have you going to infinity or negative infinity, depending on which, whether you're going towards infinity or whether x is going to infinity or negative infinity. Okay, so if you know that there's a slant asymptote, there's no need to check for a horizontal. Now, how do we find the slant asymptote? Well, we find it by knowing that a fraction is just a division problem. So I'm doing x squared divided by x plus 1. For this particular example, because that's just one copy of x and a number, if I wanted to use synthetic division, I could. That's a nifty shortcut. I would suggest that you make sure you know polynomial division, because if there'd been just a 2 in front of that x, or if this had been x squared and the top had been x cubed, I'd have to use long division. So make sure you know that first. That's your biggest priority. If anybody wants to review synthetic division, it's a lovely shortcut. If you don't remember it and you want to run through it in office hours, just let me know. Okay. All right, I'm going to work this out using long division. So I just look at the lead terms and I say, what would I multiply x by to get x squared? And I'm thinking x. So then we multiply. So I get x times x is x squared. X times minus 1 is minus x. Okay. So I multiply by the whole thing. I figure out what to put up here by looking just at the lead term, but I multiply it by the entire thing. Now we want to subtract. I usually think of that as change the sign and add, because I have to remember to distribute that negative sign. So the x squareds cancel, I get an x. If there were additional terms, I'd bring down the next term. There really isn't. So I say, okay, what would I multiply x by to get x? I'm thinking 1. So I add a 1 there. 1 times x gives me x. 1 times negative 1 gives me a minus 1. I subtract, which means I change the sign and add, and I get a 1. So that's my remainder. But what we do with that remainder is we write it as plus 1 over x minus 1. It's kind of like if I were doing 7 divided by 3. I would say that goes in twice with 1 left over, and that would become and 1/3. Okay. Now, we read that as 2 and 1/3. The addition here is implied. The addition here we actually have to write out. So this function is the same as x plus 1 plus 1 over x minus 1. That's what that long division gave us. And this right here, the x plus 1, that is our slant asymptote. And the reason is that the function is just the sum of these two terms. But if I look at this term is going to go to 0 as x goes to either plus or minus infinity. So in the middle of my graph, this term might significantly affect the behavior of the graph. But on the outskirts, this part is really, really small. So we're really, really, really close to this line. Now, The reason it has to be that the degree on top is 1 more than the degree on bottom is just so that when we do our division of the lead term into the lead term, we simply get a multiple of x, because that's going to give us a linear function. If they differed by 2 or more, I could get a curve, like I could have a parabola that was my asymptote. In this textbook, we're really just looking at slant asymptotes rather than what are called curvilinear asymptotes. Okay, so when I go to graph this, I'm going to graph y equals x plus 1. So the y-intercept is 1, up 1, over 1. I'm going to graph that as a dotted line. That's going to be my slant asymptote. Now, with slant and horizontal asymptotes, we are allowed to cross them in the middle. We're even allowed to cross horizontal asymptotes as we go off infinitely far. Okay. So I can cross this. This is mostly going to be important in determining the end behavior. Some of the homework might ask you to find out, does your function ever actually cross the asymptote? We could actually check that really quickly here. Okay. So if I ask, do we cross the asymptote? Now you can't cross a vertical asymptote, but you can cross a horizontal or a slant. If we did, that would mean that x squared over x plus 1 would have to equal x plus 1 at some point. Well, that would mean that x squared would equal x plus 1 squared. So no, we don't actually cross this one. There's not going to be any solution to that. Okay, so that gets us our slant asymptote. Now I'm going to keep going with this, but if you stuck with me from the beginning of the video, I would suggest you pause now, try to do the rest of the problem, then tune back in and check your work. Okay. All right, so let's find some intercepts. If I want to find the y-intercept, I'm going to plug in 0. So I'm going to get 0. So that tells me that my y-intercept is just the origin. So I can plot that point. If I look for any x-intercept or sets, I'm going to set the function equal to 0. So x squared over x plus 1 equals 0. That would imply that x squared is 0 and x plus 1 isn't 0. Well, that's going to be true if x is equal to 0. So I knew the origin was an x-intercept. It turns out it's the only one. Okay, we've already found our slant asymptote. Let's check for vertical. With rational functions, I definitely want to take a look at what makes the bottom 0. And I can see negative 1 is going to make the bottom 0. So I'm going to have a vertical asymptote at negative 1. Notice this slant asymptote of x plus 1 is going to cross the x-axis at negative 1. So the two asymptotes intersect at the x-axis there. Okay, so that's the information that we're going to get from f. Let's go ahead and take a look at f prime. So f prime of x, we're going to use quotient rule. So that's going to be low, x plus 1. D high is 2x minus high is x squared. D low, excuse me, D low is just 1. Okay. All over x plus 1 squared. So that's 2x squared plus 2x minus x squared all over x plus 1 squared. That's going to be x squared plus 2x all over x plus 1 quantity squared. Okay. That is always defined on our domain. Of course, it's not defined at negative 1, but that wasn't in our domain. So let's take a look at where that's 0. So if f prime of x is equal to 0, that's going to mean that x squared plus 2x is 0, and x plus 1 squared is not 0. So the top is 0, bottom isn't. Here I can factor. That's x times x plus 2. So that's going to give me x equals 0 or x equals negative 2. So I've got 2 points to mark off because they're critical numbers, negative 2 and 0. I'm also going to mark off -1 because that's a vertical asymptote. Now I'm labeling that it's a vertical asymptote. If the derivative changes sign here, there won't be a max or a min, but I definitely need to check because it could change sign on either side of that asymptote. So let's pick some test numbers. Okay. If I try -3. Now notice that with our derivative, the denominator is always positive because we're squaring it. Okay. So I just need to see what the top is. So let's see. That's going to be 9 minus 6. That's going to be positive. Between -2 and -1, I'm going to try -3/2. Okay. And here might help to remember that that was x times x plus 2. Okay. So -3/2 is negative. -3/2 plus 2 would be positive. So that's going to make that negative. Between -1 and 0, I'll try -1/2. Okay. That's negative. That's positive. So we're going to have something that's negative. And to the right of 0, let's just plug in 1. Positive times positive is positive. And of course the denominator we said was positive. So we're going to go up and then down and then down and then up. Okay. So at -2, it looks like we're going to have a max, and at 0, we're going to have a min. Now, I already know the value at 0 right here, so I'm just going to indicate that that's going to be a low point, so that when I connect the dots, I remember to treat that as a low point. Let's figure out the value of our max. So if I plug in -2, and remember I'm plugging into the original function because I want to see how high up to put that maximum point, that's going to give me 4 over -1 or -4. Okay. So I have a max at -2, -4. When I go to plot that, I want to make sure that I plot that on the right side of this asymptote. So let's see, the asymptote was x plus 1. So at -2, this would be at a height of 1. -2, -4 is definitely below that. So I've got a max down here at -2, -4. That's kind of good because we just determined that we weren't going to cross this asymptote. So very good that my max isn't above it, because then I'd think I'd probably cross it at some point. Okay, so that's what we get from f and f prime. I'm going to stop the video and come back in the next video to do f double prime in the concavity.